All right, welcome to Specific Heat Calculations. I got a question for you. If you just heated your pizza for 20 minutes and let it cool for 1 minute, what is more likely to burn your tongue, the cheese or the sauce? So think back. If you chose the sauce, you'd be right. Let's take a look at something. So specific heat, just a quick definition of it. Specific heat is the amount of energy to raise needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. So things that have a very high specific heat, those things heat and cool slowly. So all that means is it takes a lot of energy for that to change the temperature of something, right? So it takes a lot of energy for that to heat up, it takes a lot of energy for that to cool down. Low specific heat, those are things that heat and cool quickly. So again, what that just means, it doesn't take that much energy for that to heat up or for it to cool down. So some examples of that is water for high specific heat and common metals for low specific heat. So thinking back to that first question, with pizza sauce, it has a really high moisture content. So its specific heat is similar to water. So it's something that takes a lot of energy for it to heat up. And once it's hot, it takes a lot of energy for it to cool down. So so it takes a little bit of energy for that to cool down. So that's why that one would be more likely to burn your tongue. So if you're ever eating pizza, especially if it's really hot, you know that burn. Um, Another thing to think of this with is a pot of water. If you've ever boiled water, the metal on the pot, right, is going to heat up quicker. That's more likely to burn you. And it takes a while for water to start boiling up. All right, so that's a little bit of background information, a little bit more with heat. So heat's just a form of energy. It's measured, or two of the units are calories and joules. Um, when you look at a nutritional label, you see calories, right? So calories kind of indicate energy, right? So energy unit calories. Those nutritional calories are related to these chemistry calories. So the conversion for it is for every one nutritional calorie, there's 1,000 chemistry calories. So they might have not used the chemistry calories because that's a lot. It's a big number we'd have to put in those nutritional facts, right? So instead of seeing that number 250, that's equivalent to 250,000 chemistry calories. Whew, that's a lot. All right, so with that, we're going to take a look at our specific heat equation. So specific heat equation is Q equals MC triangle T. Some people refer this to as Q equals MCAT because the triangle is like an A, I guess. All right, so Q, what Q stands for is heat. And so again, the unit for heat is joules or calories. And that's going to depend on something, or that's C. It's going to depend on that specific heat. M stands for mass. So mass, unit for mass is grams. C, specific heat. So this is a tough one because you wouldn't think C is specific heat. If you ever spell specific heat wrong, cuspific, that could work, right? Cuspific heat. So this one depends on the substance. So just like how mentioned before, some substances heat up really quickly, some heat up slower. So each substance have their own specific heat. And then lastly, triangle T or delta T, as some say, change in temperature. So this unit can be degrees Celsius or Kelvin. And to find change in temperature, you're just going to take the final temp minus the initial temp. All right, so this is the equation we're going to use. So let's go and take a look at an example problem together. So what quantity of energy is needed to raise the temperature of a piece of copper with a mass of 95.4 grams from 25 degrees Celsius to 48 degrees Celsius? All right, let's go ahead and we're going to box. We're going to be looking for energy in this problem. And we have a piece of copper, so that might be important. Let's just underline that. And we're definitely given a mass of 95.4 grams, and the temperature is going from 25 degrees Celsius to 48 degrees Celsius. All right. So with problems, I always just like to write the equation out first. So I'm going to go put Q equals MCAT. All right. So if we wrote down this equation, Q stands for our heat. Let's see, do we have our heat in the problem? What quantity of energy? No, so that's what we're looking for, right? So it's asking what amount of energy. So Q is going to be our unknown variable. Let's see, do we have M? So M stands for the mass. Yeah, we have the mass of our substance. So we have 95.4 grams of copper. All right, C. Okay, what does C stand for? Caspific, right? So if we're spelling it wrong and saying it wrong, my goodness, is there a way we can find the caspific heat of copper? Whoa, look at that table over there. So again, these have their own value. So if we look for copper, copper is right over here. The specific heat for copper is 0.38. So we can put 0.38. If we notice the unit for specific heat, it's given to us right over there. It's joules per gram degrees Celsius. I'm going to write down these units just to show what's going to happen to them. All right, so we got 0.38 joules per gram degrees Celsius for our specific heat. Lastly, we have the triangle T, so the change of temperature. So we want to find our final temp and minus our initial temp. We want to find the change it went through. So let me write something here. Triangle T. Let's change colors. Let's go with green. All right, so triangle T is TF minus TI. All right, my final temperature is 48 degrees Celsius. And my initial temperature is 25 degrees Celsius. So I'm going to just take 48 minus 25. That's going to give me 23 degrees Celsius. All right, let's go and write down what we have so far. So we got Q, that's what we're looking for. We got 95 grams, 95.4 grams, 0.38 joules, grams, Celsius, and we have 23 degrees Celsius. All right, so we have these three numbers all next to each other. So if we know math, right, like they're just gonna get multiplied together. So it's gonna be M times C times change of temperature. So we're gonna put 95.4, let's get our calculator. So 95.4 times 0.38 times 23. Couldn't read my handwriting for a second. All right. So we should get Q equals 833. All right, so our Q, our energy, it's going to take 833. All right, we need a unit on this. So again, if we think back to what our units for Q is, it's joules or calories. In this case, since our specific heat has joules in the problem, or joules as the unit, our unit's going to be joules. If you want to see how they cancel out, if we have grams on the top and grams at the bottom, those, if you take something divided by itself, it's going to be 1. Same thing with our degrees Celsius. So we're going to be left with J anyway. So for this problem, let me make my Q look better. It will take 833 joules to change the temperature of copper, of 95.4 grams of copper, from 25 degrees Celsius all the way up to 48 degrees. All right, so that's just how much energy we would have to put into that. All right, there are 3 U-try problems here. 1 and 2 are really similar to what we did. Number 3, it's a little bit different. I think you can do it. So go ahead and pause the video. Try your best on 1, 2, and 3. And after you pause it, we'll take a look at these answers. It's paused, right? Okay, I believe you. All right, we're going to resume here. So hopefully you've tried those answers and you've unpaused it. So for number 1, we should have gotten 12.3 joules. So 12.3 J. Number 2, let's read that handwriting, 773 joules. And our last one, the last one was tricky, right? We had to look for something else. So we were given actually Q. So we were given 50 joules of energy. So if you guys got granite, you would have been correct. Yay. If not, let's run through this one. But if you got it, awesome job. So again, I would just write my equation. Q equals MCAT. This time I'm given my joules. So I'm given 50 joules, given my Q. I'm also given my mass, 3.17 grams. I don't know what the sample is, so I'm not going to know its specific heat or specific heat. But I do have the change of temperature. So it's going from 0 degrees Celsius all the way up to 20 degrees Celsius. So if I take my final minus my initial, 20 minus 0 is just going to be 20. All right, so now we're just going to do some math. We have two numbers on the right side that can be multiplied together. So we're going to take 3.17 times 20. Okay, so if I'm writing this down, I got 50 equals 63.4 C. All right, so I'm looking for this variable C, right? So this is my unknown because I don't know what sample it is. Now I want to just divide by both sides. The number I'm going to divide it by is whatever's attached to the variable. So I'm going to take 50 divided by 63.4 equals C. So let's go ahead and plug this in. 50 divided by 63.4. All right, so I got my C to be 0.789, around there. All right, so looking at 0.789, taking a look at our specific heat table, what's the closest to that? Yep, we stop right there.